The rates of change, this is from Sadler Unit 3, Exercise 2B, if you want to find some questions on it. So we've already done sort of rates of change. This is just one more example of it. So rates of change is looking at differentiating and finding how something may change over time. So you might have a population of bacteria. If you have a function for n which says the population of bacteria, if you differentiate, you can find their growth. So when t is 1 second, I can use my formula to find out whether my population of bacteria is growing or whether it's decreasing, right? Which is good if you don't want to get poisoned if you're eating a sandwich, for instance. So this is our question here. A colony of bacteria is increasing in such a way that the number of bacteria present after t hours is given by n, where n is equal to 250 plus 100t plus 50t cubed. So find the number of bacteria present when t is equal to 5. So this is just simply using the model. We're going to plug in t is 5 into our model. And out comes 7,000 bacteria. So after, we can see t 5 hours, so this is after 5 hours, there's 7,000 bacteria, okay? Now, this isn't really giving us a picture of how the bacteria population is changing, it's just saying how many there are at a point in time. So if we want to find that, we would need to find an expression for the instantaneous rate of change, which means dn by dt. So this is the number of bacteria per hour. That's what that function's saying. Let's differentiate 100 plus 150t squared. And there we go, we found an expression there. And so this expression is saying the number of bacteria per hour. Now this is an instantaneous thing, okay? So at any one value of t, you can find anything. Could be t, could be 4, 3, 1.6. You can find the exact increase or decrease in bacteria per hour. Instantaneous. Okay, let's move on to C. The rate the colony is increasing. So we want to see whether the colony is increasing or decreasing when t is equal to 2. So we're going to plug in to this here. And out comes 700 bacteria. And then, oh, this is I, sorry. And when t is equal to 10, I'm just going to plug it in there. I think we know what we're doing here. It's 15,100 bacteria an hour. Okay. Now, overall, we can actually see, we can model this with a function as well. So we've got the rate of change. We can see it started off at when t is equal to 2, or t is equal to 0, it had 100 bacteria per hour. When t is equal to 2, it went to 700 bacteria per hour. When t was 10, it went to 15,100. So we can see that the amount of bacteria per hour is increasing, okay? Now, if you want to see that increase and visualize it, you could always sketch this function here so we can see it's going to be a quadratic and it's going to be shifted up 100 and it's going to be quite steep. So you'll get some kind of function like this, really steep quadratic, and this will actually say the population change over time. If you wanted to visualize it. Thank you very much. I hope this video is useful, and that ends the rates of change. In the next video, we'll be looking at differentiating exponentials.